Okay. So we were talking about um, logistic regression, right? And the first model in classification. Okay. So though it's called logistic regression, it is used for classification because it first uses linear regression concept, and the output, whatever output you get, that is converted into 0 or 1 using sigmoid function. Okay. And then we saw how to, take the data set, perform those basic pre-processing steps, which is very similar to what we do in regression. Okay, then we did the prediction, and now we want to visualize how the outcome has come. So in visualization, you see, okay, we took the data from zero, not from zero, sorry, from minimum to maximum of, yeah, we have two x's here, age and salary, right? We removed gender from our analysis. So it is from for age, we moved from minimum to maximum, and similarly, we did same thing for, yeah, and same thing we did for the other X also, salary. Okay, so we are going from minimum minus 1 to maximum plus 1, and at a gap of 0.01, we are predicting, okay, we are predicting for each and every value. So when we run this, okay, and the the second, I think some different program has run. Wait. So when we run this, okay, and it's still taking time. First time when you run, it takes time. Oh, there are error. Error because it's not able to read the link today. So, okay, sometimes it happens. So it says connection. It could not make connection to this data set. Okay. So what I will do, I will take the data set from our local machine. Okay. It's in D drive data set at 5 Yes. So I will say here link equal to, okay, double backward slash, and then I'm going to copy this. Okay. Um, Done. Okay. So now it should work. So you see, you get a um, graph like this. Okay. So what does this graph indicate?
Two planes.
Two planes exactly, and the colors?
One is in negative and is in positive.
No, that's the values here. But what does this indicate? This is not positive, negative.
Mm, 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 mm. No idea.
What did we do yesterday?
I don't know. मैंने उसको रिवाइज नहीं किया था.
Vinay, you were there, right?
Mhm. We remove the call.
So we are taking each and every x value and predicting for it. So this is the value that is being predicted. Okay. See, this is the value that is being predicted. Now, if you, what did we say that the values, okay, using logistic regression it is getting, converted to 0 and 1 using sigmoid application. So what you see, this is your sigmoid application. Okay, what it says is this line that you see is straight line. Okay, and then so this line is again regression line, but this line goes from 0 to 1. Okay, which is green is 1 and red is 0. So we are taking each value and we are predicting using the model that we created. So we are predicting using the model. Okay, these are prediction that we made for every value at a gap of 0.01. So we started with 0 or maybe -1, right? We started with this is -2. So this should be -3, isn't it? So we started with -3, okay? Then -3, -3, then -2.98, right? Or 9901, right? So 0.99, then 98, then 97, okay, up to 0, then 0.01, 0.02, up to 3. Okay, so we predicted for each of these values, okay, and this is what the model is giving. This is the prediction, this is the output. So what it says is if your age, because we did scaling, that's why we see values between -3 and +3. So what we say is if your age is anywhere less than, let's say, 1.8, and okay, and these are your salaries on y-axis, then this is what you're predicting. So these people will not buy your product, and green people are the ones who's going to buy your product. This is what our model is indicating. So this is the prediction. Now we have to plot on it. We will plot on it the actual value, okay, of the training data. So this is the model prediction, and we will plot on it the actual value of uh, the training data, right? So let's see. Okay, so we have created this contour F, so this is enough. Now on it, okay, we will so now we will plot. You can plot training data, you can plot test data. So for I comma j, so I'm going to run a for loop to pick value, okay, enumerate, okay, because we have y set and x set, right? So we'll take actual value from y train and x train. So this is plotting x train and y train. You want to see? So what we just saw was the prediction, how the prediction was made. But the actual data, training data may not be that way, right? So actual data will take actual value the from the data and we will plot it here. So I'm saying I comma j, okay, enumerate, and here, okay, we will say np dot unique. We will take unique value, okay, from y set, okay, and now we will plot the graph. So plt dot scatter, right? We will plot the scatter plot. And here I'm going to use your x set and your y set. So x value, right? So one x value. So this y is what we are going to plot. That's the value. But where will this y fall? Y will fall for corresponding x1 and x2. So we have to put our first x1, okay, which is again from x set only, right? And then we will put the second on second axis, which is again x set only. But x set has two dimension, 0 and 1. So we'll put first 0, which is age, and dimension 1, which is our salary. So I'm going to say here X set, and your Y X set is also small, I think. Yeah, that's why it's giving it. We have taken X set also as small. Okay, X set, and then you have Y set. Okay, Y set equal to J, the second value, right? And 0, 0 indicating your age. Okay, now this is your first X. Okay, they should go by here. And same thing, we'll take it here. And this time, instead of 0, we'll put 1. Okay. And color. Okay, we want to put the color of the dots. So I'm going to say color, okay, equal to listed color map. Okay. And we will give values as tuple here. Now for 0, let's give some light color. Let's say we give yellow, and we'll give pink. Okay. Now, in fact, we'll do yellow and pink. So for 0, there it is red, right? And 1 is green. Here I'm saying yellow is 0 and pink is 1. Okay. Okay. And then we'll change it back. I'll just show you, and then we'll change it back to red and green only. Okay. Okay. So pink here, and for each value of I. So for each value of I. So I'll put I here. That's it. And if you want to put label, you can put label. Label is our J value, right? That's what we are plotting. Okay. Should be okay. Let's plot this graph. So you see this? Okay. The yellow ones are actual, no. So most of the yellow ones are falling in red area only. Pink ones are actual yes. So the pink ones falling in red area are the ones that your model got it wrong. Those are the errors basically, right? Okay. Now what I'll do, I'll convert it back to red and green, so that what happens, the red will match to red and green will match to green. And what we will see is just the green in red area, red in green area, which is easy to identify the errors now. So see, the red here will match to red. So, we don't have to, okay, we don't need to know the problem. And here you see, these are your error. These are the green area from the training set. See, this is the line. This is the regression line which our last regression has predicted. And the values which fall, these are the ones which model is saying that they will not buy, but they actually bought. No, they will not. Yeah, red is 0, right? They will not buy. They actually bought. So remember day before when we were speaking about model evaluation, we said that we will create two-dimensional uh, metrics, right? To evaluate the classification model. Okay. So red falling in red area are actual no, predicted no. Green falling in green area as actual yes and predicted yes. Okay. Green falling in red area are actual what? Green falling in red area are actual, green means actual 1, but we predicted as 0. This is your error. Similarly, red is the one that we predicted yes, but they did not buy. They are errors. Okay, so they are actual no, but we predicted yes. So this is the error. And okay, now we will evaluate the error. But any question here so far? Did you understand what I did? Okay, this is how we can visualize the model and see if it is okay. You can actually see the output here. Yes? Yes or no, guys? Tell me. Don't sleep in the class. Now we will evaluate the model, let's say. Okay. Now, model evaluation, what I said, we use 2 by 2 matrix, and that is called as confusion matrix. Okay. Confusion matrix. Okay. Now we are going to use confusion matrix. Okay. Now, this is how we generally evaluate classification model. Okay. So again, this is part of your sklearn. So from sklearn, okay, dot matrix import what? Classification report. Okay. Then we'll say confusion matrix. And then we will say accuracy score. Okay. These are the different values or the metric that we need. Just like we have R square, RMSE, okay, MSE. Okay. These are similar to what we have there. Okay. Now, before I actually talk about it, let me take you through my notes. Okay, let me open my notes. Give me a second. I'll open my notes here. Um, just give me a second. Got it. Can you see classification algorithms? Okay. No. Okay. Choosing the right model. Yes, here. Okay. Now, this is an example of confusion. Do you see the matrix? Yes or no?
Yes.
Yes. So this is an example of your confusion matrix. Okay. So you have here actual value, no, yes, and predicted no and yes. In this example, what we have done, we have predicted no, actually no, and predicted no. Here, this is actual no and predicted yes. Actual yes, predicted no, and actual yes and predicted yes. These are the 4 possible values you get. These are the 4 possible values you get. Now, if you see this, okay, so we have something called as TN. that is true negative. True negative, false positive, false negative, true positive. Okay, how do we read these values? Okay, the negative or positive, okay, negative is or positive is based on what you predict. Okay, because we are here to predict. So what we predict is taken as negative or positive. True and false is whether we got it right or wrong. So if you say no here, okay, when we say no here, okay, and actually it is no. So our prediction is right or wrong? Our prediction is correct. So we call it as true. And what did we predict? No, negative. No, they will not buy. Okay. So negative means no, right? We're saying no, they will not buy, negative. So when you say negative and it is correct, it became true negative. That's what TN. TN stands for true negative. Okay. So true because you got it right, and negative because, okay, you predicted no. Okay. So you predicted no and it is no. So true negative. Okay. Here, what did you predict? No. But it is actually yes. So it is going to be negative, but you got it wrong. False negative. Okay. So true positive is based on whether you got it right or not. True means you got it right. False means you got it wrong. So whenever you see false, that means that's an error. When you hear true, that means that is correct. True what? Negative, because I predicted negative. Okay. True. So this is true positive. This diagonally opposite is true positive because I got it right and I predicted positive. So it is true positive. So true negative, true positive, and this opposite is false positive year 10 because I got it right. No, I predicted yes. So that's why positive. But did I get it right? No. So it has to be false. So you have false positive here. Very clear?
Yes.
Okay. So you have false positive here and false negative diagonally opposite. Okay. So there are so when you call confusion matrix will take the data. Okay. So when you have these 4 types of values, okay, this is called confusion matrix. And these 4 types of values, okay, is shown when you perform confusion matrix. Okay, confusion matrix will calculate all, incorrect and correct values and will give it to you in a matrix format. Okay, so this is one. Now, how do we come up with different metrics? Okay, so there are some metric here which can be derived from confusion matrix. First one is called accuracy. Accuracy means how many values you got right. So how many values do you get right? Okay, you get values which are true positive and true negative, right? These are the values that you got right. So accuracy means it is true positive. True positive is 100 plus true negative, which is 25. So true positive plus true negative, that is 125 divided by total values. Total value in this case is 200, right? So 25 plus 65 plus 100 plus 10. So 125 divided by 200 is your accuracy, which is 60%, 60.25%. Okay, this is called accuracy. Similarly, you have misclassification rate. Misclassification rate, okay, is opposite of accuracy. Okay, it's like, okay, what is the error kind of? This is the error value in classification. So all false values, false positive plus false negative by total, or you can say 1 minus accuracy. Okay, so in accuracy, we're talking about all positive values okay, I mean not positive, all true values, okay, which we got them right to a total value. Misclassification is opposite. So 1 minus you can say, or you can calculate as all false values divided total. Then we have sensitivity. Okay. What does sensitivity means? Sensitivity is true positive rate. What is the true positive rate? Also called as recall. Okay. Sensitivity or recall. Okay. This is like only true positive by actual yes. Okay. Now, why do we measure this? Okay. What's the purpose of measuring only say true positive or false positive or true negative and true positive? Why do we need this? Accuracy should have been good enough, right? Accuracy should have been good enough, right? But no, let's take a case here. Okay. Let's see this. Okay. This is, let's say there are 200 questions. Okay. And this is student A. Student A has gone and thought and attempted all these questions. Okay. So let's say this is your entrance examination, engineering entrance examination. Okay. And this guy is appearing for this exam. And it's like, let's say you have 200 questions. All 200 questions are true and false. Let's assume. So this is like you said false and it was false. You got 25 marks, 25 questions. You got it right. So these are, you said true, but all these are actually false. So you lost 65 questions here. 10, this is what you said. You predicted, no, you said false, but actually they were true. So you lost 10 marks here. And here, okay, 10, 100, they were actually yes, and you predicted true only. So, this is what you marked as true, and it was true. So your score would be 60%, right, in the entrance exam. Let's take another student. Another student went and blindly what this guy did, okay, marked everything as true, 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 true. This guy has, taken effort, time, pain to mark each and every question, okay, solved it. So got 60%. This guy went and marked everything as true, 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 true. So what is the score of this guy? 82%. Okay. Now, who is better? Student A is better or student B is better?
B.
B is better?
B. Based on the percentage.
No. Okay. Student A is better. If you are a job, if you are to interview for a job, right? If you want to hire somebody, you will hire somebody who's thinking guy or who just blindly put something. This guy has blindly put true, true, true without even thinking, right? Now, okay, this guy has put an effort, has thought, okay, scored 60. So this is very much similar to our overfitting situation, okay? Similar to, not exact, we don't call it overfitting, but I'm just, this is called accuracy paradox, okay? Accuracy paradox is when you are believing on accuracy only, okay? Just on the marks, okay? This fellow, and that's what happens in the entrance examination. Some person might just work all C, 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 C. I'll just work all true, 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 true. And that person might get more marks than guy who's genuinely putting an effort thinking. So in reality, we need people who are hardworking, who uses their brain. In your job, these are not going to help you. You have to think, right? So here, though this guy has scored less, okay, but this guy is preferred over this guy because this guy is thinking, he's spending time, he's thinking. Maybe he got it wrong. That's okay, but he's thinking. We want algorithms which thinks, okay, human being that see advantage of if this monkey can do it, isn't it? Monkey will go and enter, or whatever, press any key. So we don't want a monkey, okay? We want human being. Human being can get wrong, right? But if you get it wrong first time, right? Like Chandrayaan, you can get it wrong for the first time. But if you are thinking, if you're a human being, you'll get it right second time. But if you just do whatever, right? And so this is monkey behavior, okay? In computer science, I mean and probably Vinay would know, we call them as monkey testing. Monkey testing is, you take that application and you start hitting any key. You take, let's say your company has developed a website for airline booking. Okay. So you expect enter your name, enter your destination, but you just go and start hitting any key. You want to see how resistant your website is against that kind of a thing, right? So, we don't want monkeys to make prediction, right? This you can do like Inky Pinky Ponky, right? What's the fun of building these models? We want our models to think, and it's okay if you get it wrong, okay? Because you get it wrong, you again train it, again you improve it, okay? You can do it. So this guy, student A, is better than B. Student A is thinking. Student A can get it wrong. So in this case, you see this guy. See, when you see this, there is no false. So definitely when you look at the answer sheet and you see this guy has marked everything yes, okay, then definitely, okay, there's something wrong with his attempt. You can't mark all 200 questions as true, 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 right? So this is called accuracy. If you look at just accuracy value, so this guy will appear very, very smart, 82%, 82. Okay, this guy got only 60%, right? This guy will look very smart. That's why we just don't go by accuracy. This is also called accuracy paradox, okay? That's why we go and check what is your precision, what is your sensitivity. Now, if you see sensitivity here, TP is true positive by actual yes. So actual yes is only 165. And your TP is also 165, 100%. Okay. So here in this case, sensitivity is 100%. Okay. Good. Hold it. I mean, we can't make, this we cannot go and answer, we can't go and see each and everything, right? We have to depend on the data, right? So accuracy, okay, one. Second thing is look at sensitivity. So sensitivity will tell you 100%. Okay, let's see. Let's see sensitivity. Okay, now you see sensitivity. Sensitivity in our case is true negative by actual no. So actual no was 35 and true no 0. True no is 0, isn't it? 0 by 35 will give you 0. So now you see, okay, sensitivity is 100% and specificity is 0%. So along with accuracy, you're also looking at sensitivity and specificity. Sensitivity is 100% and specificity is 0%. The higher the gap between these two, that means your model has been more like your overfitting kind of model. Is not thinking. Okay. So this is wrong. Your gap between, they cannot be exact same, right? But the gap between them should be less. Okay, had this been 70%, 50%, we would have still given benefit of doubt. 0 and 100 is extremes, right? So even though the accuracy is high, and if you see the sensitivity is 100%, specificity is 0, or reverse, okay? This guy could have gone and marked all no, 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 no. You marked all no, 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 then specificity would have been 100%, and sensitivity would have been 0%. TP is 0. True positive is 0. Never got not one right. So there, okay, if the gap is very high, you reject that model. So you will reject that student even though the student has got 80%. Okay, because that guy is not thinking. That's the message that you get. Okay, so that's where sensitivity and specificity also you should look at along with accuracy. Accuracy is the overall score. Yes, accuracy is main. But whether should you accept that result or not, for that you have to look at specificity and sensitivity. Precision, prevalence is different. Okay, actually yes by total, right? Okay, these are all different versions of same thing what we discussed. So look at all these 4-5 metric: accuracy, sensitivity, specificity, and this is precision. Precision in this case will be 0. TP, true positive, is 0, right? No, sorry. In this case, okay. In this case, precision is not 0. So precision is true positive. True positive is 165 divided by predicted yes. That means you got 100% right on yes. Predicted yes is 165 and true positive is, okay, That means you predicted 165 and all of them turned out to be true. I predicted 165 and all of them turned out to be true. Now, this is 100% accuracy with all the yes questions. Now, if you get 100% accuracy, then the precision and prevalence both will be 100%, right? So this is what precision is. Precision is that, you are very good with all the true. Specificity is 0. Okay. Actual no is 35 and true negative is 0. Specificity is 0 means you are all wrong. You are doing very bad with no's, false answer. So if the answer is false, you are not able to predict. If answer is true, you are able to predict 100%. This is what precision will tell you and specificity will tell you. How well you are with true data, how well do you do with false data. Did you understand? These are the metric that we use, okay? And that's I just give an example why we don't just go by accuracy. We need to measure sensitivity, specificity, okay, precision, prevalence. These will tell you, okay, how this model works. So here, confusion matrix is again very important, and not just with machine learning. This is a general statistical phenomena, and many of your examinations and anything that you do related to mathematics, this is a common question they'll ask you. Okay. Okay. So this is called as measuring the value. Okay. Implying, okay, how the output has been generated. Okay. So again, just like regression here too, you'll have to run multiple algorithms. You have to run multiple algorithms and then figure out which one is better algorithm. So one is creating confusion matrix and calculating at least 3 things. What? Your class accuracy, sensitivity, and specificity. You want to further drill down, you can go to precision and prevalence. Okay, but at least A and double 2S, sensitivity and specificity. So sensitivity is also called as TPR, true positive rate. Okay, and specificity is calculating DN. Okay. Okay. Okay, so this is one way to measure. And second method to measure the performance of your model is called CAP curve. Okay, cumulative accuracy profile. Cumulative accuracy profile. Okay, we'll do that. Now, before I get into that, there's one more concept here we need to understand. Okay, let me see if it is there here. No, okay, so we directly go to CAP curve. Okay. Okay, just give me a second. I will open it here. Type 1 and type 2 error. Okay, so you have 2 error, right? Okay, which are those 2 error? False positive and false negative, right? We have 2 errors, false positive and false negative. Okay, now they are called as type 1 and type 2 errors. Okay, okay, here. Okay, now here you see, this is reality, this is actual, and this is your perceived or predicted value. Okay, predicted value. Now, reality is true and you predicted true. So true and true is going to be, what do we call this as? True positive. Yes or no?
Yes.
This is a true positive, okay? It is, reality is true, predicted is true, so true positive. Here, reality is false, you predicted false, so it is true
Negative.
negative. Now here, I predicted false. So I told you, okay, the false or true is dictated by whether you got it right or not. So this is what you got it wrong. So this is false, right? Actually, it is true and you predicted false. So answer is false. False what? What did you predict? I predicted false is 0. So negative, I predicted negative. It's called false negative. False negative. And here this is called false positive because you predicted true. Yes, positive. Okay. but you got it wrong. So false positive. So you have false negative and false positive. These are your two errors. Okay. Now, false positive, okay, false positive is also called as type 1 error. And false negative is also called as type 2 error. Okay, type 1 error, type 2 error. Okay, now this is used in variety of fields, okay, whether it's about marketing or, testing, and whenever you're doing any kind of testing, okay, this concept is useful, even, any analysis. So false positive, when you predict P, when you predict 1, it is called 1, type 1 error. Okay. So this is how I remember. 1, 1. If you predict 1 and you got it wrong, it is type 1. And 0 is 2, even number, odd number, even number, right? So I said 0, but I got 1. So it is even number. So type 2 error. Now, why this is important is both are errors. Okay. But in both the errors, which is more dangerous? Okay. Now let's say, okay. Now let's say a person, okay, goes to doctor, okay, for some problem. And let's say doctor suspects cancer. Okay. I'm just saying an example, extreme example, okay, so that you understand the difference between type 1 and type 2 error. Person goes to doctor and doctor suspects cancer, right? Now, doctor is suspecting cancer, right? So when doctor is suspecting cancer, that means if it is true, that means if person gets cancer, only it is positive. Now, positive, negative doesn't talk about the news, right? Okay, getting cancer is negative news, right? But positive because doctor is suspecting, so it is positive. No cancer or yes cancer. Okay. So doctor is suspecting cancer and person does not have cancer, right? So this is better because doctor will go for some test. Okay. And then let's say you come out later saying that person does not have cancer. But look at the other scenario. Doctor does not suspect cancer. So, oh, you're fine, go home. But person has cancer, right? So what happens generally? False negative is more dangerous than false positive. Any situation. And that's why in our life, when it is 50-50, we plan for problem, we plan for error, right? Why do you, let's say if travel time from your home to airport is, let's say, 1 hour. Okay, if your travel time from your home to airport is 1 hour, we start 1.5 hours before, 2 hours before. Okay, it's okay to reach the flight. Okay, oh, will I miss my flight or will I not miss my flight? It's okay that you reach early and not miss your flight, then you reach late and miss your flight. Type 2 error. Okay, so false negative is more dangerous. False negative is what we don't want. False positive is again error, but it's okay to have this error. See, you cannot predict 100% accurate with 100% accuracy. Okay, you can't predict with 100% accuracy. If we can predict 100% accuracy, you look at Google Map. Oh, map shows 45 minutes travel time, and you'll start at 45 minutes only. But we know that in reality, we cannot predict 100% accuracy. If a Google Map shows 45 minutes, you will start 1 hour before or 1.5 hours before. You will not say, oh, Google Maps says 45 minutes, I'll start exactly 45 minutes before time. Okay. What you're doing is you're trying to mitigate this type 2 error. It's okay to reach place early. It's okay to reach airport early. It's okay to fall into type 1 error than get into type 2 error. Okay. Pilot is suspecting some problem with the engine before takeoff, right? So pilot says, no, I'm suspecting some error. Please check. Okay. And engine turns out to be fine. No problem. It's okay. That is type 1 error. Then pilot says, okay, no, engine is fine. Everything is fine. Let's fly. And the problem gets in the air. That is type 2 error. You say no, but it turns out to be yes. So typically your type 1, type 2 error, if you see, okay, it is your type 2 error is what is more dangerous typically. Okay, most of the situation. Okay. So it's okay sometimes, we purposely land up into type 1 error zone, then we don't want to get into type 2 error zone. This can also be represented into this graph, you see. Okay, it's called alpha and beta. Okay, alpha is called type 1 error. Okay, beta error, also you'll hear beta error, alpha error. Alpha error is type 1 error. Type 1 error is false positive. Type 2 error is false negative or beta error. So this blue is, what you say is no, null hypothesis means no. I told you, right? Null hypothesis is no. You predicted no, it is no. So it is true negative. This is a true negative area. And green one is your alternate hypothesis. You said alternate hypothesis is 1, right? So you true positive. But area which is overlapping is the problem area. Okay? Area which is overlapping is problem area. So area where it is actually blue, actually negative, but you predicted positive. Beta error. Okay? So this is your alpha error. Yes? So this is the problem with alpha and beta error. Your beta error is same as type 2 error. Okay? So that's about type 1 and type 2 error. Now, shall we move to next topic?
Yes, sir.
Okay. Now, second way to measure, okay, which model has done better is using CAP curve. Okay? CAP curve stands for cumulative accuracy profile. Okay? And as names are cumulative accuracy. Overall, what is the accuracy of this model? Okay? Now let's take an example. Okay. Since we have Ganesh Puja, right? Let's talk about Ganesh Puja, right? So let's say you have in your society, okay, this is your society, and these are number of families. Okay. So let's say there are 1,000 people who stays in your society. And you know that based on your average record, okay, based on average record, about 60% of people gives chanda for your Ganesh Puja. Okay, or 60 people will pay money for the puja, let's say. That is the, let's say, your past data. But okay, but you don't know who are those 60%. Okay, on average, we say that 60% pays chanda. Okay, but we don't know who are those 60%, right? So in normal circumstances, when you do not use any model, what will happen? You go to 10 people and 6 people will give you chanda. 20 people, 12, right? No, sorry, 100, right? 100 people, you go, 6 will give you. You go to 200 people, 12 people will give you. So that you go to 1,000 people here, 60 people will give you. So what happens in this case? So this is your 1,000, right? So you see the line that you will get is like this. You go to 0 people, 0 person will give you. 100, 6, 200, 12, so on. You go to 10,000, you will get all the 60 people who will pay you. 60% is 600, right? Why not 60? Okay, pardon me. Okay, so this is like 100, 60 means out of 100, 60 people will pay, right? So 10 people, 6 people will pay. At least you got what I'm saying, correct? So if you go to 10 people, 6 people will pay you. 20 people, 20 people, 12 people will pay you. It is 60% per 100, right? Not per 1,000. So when you reach 2,000, okay, because these are the maximum number of people who will pay you, which is 600. Okay, and this is maximum number of people that you are in society, 1,000. So if you visit all the 1,000, you will 600 people will pay you. Now in this case, you don't need to apply any model. You go to everyone and you ask for this thing and you get it. Okay, so okay, you applied what is called an average. This is very similar to if you talk about R square, in R square, what we did, we looked at the average line, right? without performing regression. We said, okay, this is the average line and this is the accuracy based on average line. Now, how well your model has performed with regression. With regression, it should perform better than your average line. That's your R-square value. Something similar, okay? Something similar here. If I had followed the average method, this is how I would have reached, right? I had to go to all the 1,000 people to get money from all the 600 people, right? Average. Now, if I apply my model should give me a better result, right? Okay. So before applying model, let's say if I know exactly those 600 people, now it's like when you are able to predict, we don't need model. You know exactly it is yes or no. Okay. So what happens? You go to one person will pay you. Go to two person. So you go to, from here, you go to 600 people and 600 people will pay you, right? 600. And let's say this is 600. So what happens? Okay. Because you know exactly who are those 600 people, right? So you don't need model. So this is average when you don't apply any model. Okay. And this is the line that you get, right? For every 10 people, 6 people will pay you. And this is the line we get. Now, when you know exactly, okay, when your accuracy is 100%, okay, accuracy is 100%, you know exactly who are the people who is going to pay you. So what happens? You go to 600 people, okay, and 600 people will pay you money, right? So these are the 600 people, okay, 600 people will pay you. And after that, you go to other 400 people, they will not pay you. I mean, this may not be the good thing. So it should look something like this, okay? 600, okay, you go to 600 people, and after that, you go to 400 people, they will not pay you, right? They are anyway not paying. So this is the best case. Best case is when you know exactly, you are able to predict 100%. And this is your average case. Average case means you're going to everyone and asking and you get you. But if you apply a model to predict whether this person, okay, flat number 101, 102, 103, 104, okay, and you have their description. Will this person pay or not? Yes or no, yes or no, yes or no. When you apply, your model will lie somewhere between this curve. You agree? This is the average model where, accuracy is 0. You go to everybody and, you have to ask them, okay? But if your accuracy is 100%, you know who are the people who's going to make the payment, okay? This is the red graph, you'll get it. But your model will be somewhere between 0 and 100% accuracy, right? So your model, okay, will be like, okay, first 80% has predicted correctly. Then it has not, okay, let me use different colors. Okay, predicted correctly for some time. And then it has, not predicted correctly. And finally, after that, you reach to a point where, this is the accuracy you got, right? So your machine learning models, classification models will have a cap curve between best fit and average case. Did you understand? Okay, you will reach 600 people, but you will reach 600 people after talking to maybe 800 people, not 600, 800 people, 900 people. The model which has cap curve closer to this line. So if you have this as model 1 cap curve, and then you have, let's say orange color I use, and there's another model here. Okay. And these are the values that model gives you. So between these two, orange is a better model than the other one, because this is closer to this best fit. This is a dream. This is, this is what you aspire for. Your model should give you 100% accuracy, but it doesn't always give you 100% accuracy, right? So cap curve tells you that if you go to one person, you're predicting this person will buy, and you go and buy. Okay, let's say model is predicting that flat number 101 is going to give you the money. So it is 1, 1, 2, 2, 3, 3. And it is predicting that 105 will give, but 105 is not giving. So 101, 102, 103, and then it becomes flat here. Because you predicted, but he's not going to give you. Again, okay, flat. So that's why you see this curve here. Okay, this means there's some error here. And you get a curve here. Okay, so the curve closer to the best fit is the better model. So it's called CAP. Clear? So this is similar to, not exactly, okay? I'm just trying to connect the dots, okay? This is similar to your R-square kind of metric, and the one that we did before, accuracy, is similar to your RMSE kind of metric, okay? So let's say here, this is the perfect model, okay? So, okay, uh, you got all the correct values in the first attempt itself, and then, if you go further, anyway, doesn't have any problem. All right. So, okay. Now, if you see in this example, SVM is gray and logistic regression is orange. So clearly, logistic regression looks better than your SVM. Okay. So area and another curve. So there is another, so you calculate the area, and there's another understanding here. Okay. It's here. Okay. If area under the curve is 60%, if less than 60%, we say rubbish model. We don't need that. If you're, that's what. So 50-50, we can do, right? Tossing a coin, right? What's the use of using the model? Okay. 60-70% area, we say poor model, generally. Your model is, when you say 99%, 98%, it is too high. I mean, it says too good to be true, right? How can you predict up to 100% or 95%? Okay. 80 to 90 is a good model. Of course, our target is to go as close to 100%. Okay. So this is how we evaluate our model. We'll see them. Okay. Now, from next week onwards, we'll run through other models. There are a lot more models that we have to cover. So next week, our focus will be on each of these models of classification model. Okay. And we will evaluate each model on these parameters, your confusion metric. Okay. So next class, we will see how to create confusion matrix, how to calculate accuracy, sensitivity, specificity, okay, all those things. Any question before we wrap up?
Mm-hmm.
No.